Where? 2/3 y to the third power. Okay, and we're going to evaluate that at 1 and 0. Okay, which is equal to 2/3. If our units were meters, this would be 2/3 meters cubed, or cubic meters. Oh my gosh, wake up. We.
Alright, so we're going to be learning about some triple integrals today. So let's get some axes up on the board here. We've got our axes here. X, Y, Z. And that's where we're going to pick up from. Alright, so this is my x-axis, this is my z-axis, and this is my y-axis. So we have x, y, and z. And if you look at it, the x is between 0 and 3. So x at 0 here, we have 1, 2, 3. Our y is between 0 and 4. So 0, 1, 2, 3, 4. And our z is between 0 and 2. So 0, 1, and 2. So you have a boundary here that's going to come in like that. Yeah, it's going to come in just like that. So we want to figure out the volume of this cube. What does a triple integral mean? So what we would do is take the volume of a very small cube, which we're going to put inside here. So that's my cube. It's someplace within the larger cube. So what's the volume of that cube? Let's say that the width is dy, and we say that the depth is dx, and then we're going to have its height here as dz. So you can say that a small volume within this larger volume, you could call that dv, so we'll put dv off to the side here, which is kind of the volume differential, and that would be equal to, you could say, the width times the length times the height. So that would be dx times dy times dz. Anyway, what can you do with it in here? Well, we can take the integral. All integrals help us do is help us take infinite sums of infinitely small distances, like a dz or a dx or a dy, etc. So what we could do is we could take this cube and add it along the up and down axis, so this axis here, so that we get the volume of a column. Alright, so what would that look like? Well, since we're going up and down, we're taking the sum in the z direction. So we'd have an integral from z equals 0 to z equals 2, which is the dz, dy, dx, with our integral z equals 0, z equals 2. So this integral, this value, as I've written it, will figure out the volume of a column given any x and y. It'll be a function of x and y, but since we're dealing with all constants here, it's actually going to be a constant value. So then, if we want to figure out the height of the column, we could take those columns and sum them in the y direction. So we've got y equals 0 to y equals 4. And then that'll give us the volume of a sheet that is parallel to the zy plane. And then all we have left to do is add up a bunch of those sheets in the x direction. So then we want to have behind that there our x equals 0 to x equals 3, coming from what we've done there earlier. And we'll have the volume of our entire figure. And to evaluate this, first we're taking the integral with respect to z. Well, we don't have anything written under here, but we can assume that there is a 1 there, right? We can assume that there's a 1 right there. There it is. because dz times dy times dx is the same thing as 1 times dz times dy times dx. So what's the value of this integral? You evaluate that from 2 to 0. And notice when we just took the integral with respect to z, we ended up with a double integral. So you could have written z from 0, integral, double integral there, 3, 0, dy dx, because you could have this written z is a function of x and y. It's a constant function, but if you had defined z in this way and you wanted to figure out the volume under the surface, where the surface is z equal to 2, we would have ended up with this right here. That's what we would have ended up with. So what you see that we're really doing with the triple integral, it's really nothing different. And you might be wondering, well, why are we doing it all? What's the point? Why would we even bother? Well, anyway, the integral would evaluate, obviously, to 24 if you were to manually calculate it. But I know the obvious question, what is it good for? This math stuff, why would we even bother? Well, when you have a kind of a constant value within the volume, you're right. You could have just done a double integral. But instead, what if I were to tell you, what if I were to share with you fine folks that our goal is not to figure out the volume of this figure. Our goal is to figure out the mass of this figure. We're twisting and turning with these roadblocks here. So even more, this volume, its mass is not uniform. If its mass was uniform, you could just multiply its uniform density times its volume, you'd get its mass. We all know that. But let's say the density changes. It could be a volume of some gas, or it could even be some material with different compounds in it. So let's say that its density is a variable function of x, y, and z, which are our coordinates there. So let's say that the density notated as p. So we're going to have this funky looking p here. We like that with the hook on the end there. It's what you normally use in physics for density. Same time science in this now. Its density is a function of x, y, and z. So we have to add to this x, y, and z. That equals x, y, z. So if we wanted to figure out the mass of any small volume, it would be that volume times the density, right? So we could say that the mass, d mass, perfect there. So differential mass, or a very small mass, is going to be equal to the density at that point, which would be x, y, z. So equal to x, y, z times the volume of that small mass. And that volume of that small mass we could write as dV. And we know that dV, we'll scrunch it in right there. And we know from our prior knowledge that that is the same thing as the width times the height times the depth. But if we wanted to figure out the mass, it would be the density. So all this equals x, y, z, dx, dy, dz. It would be the density function at that point times our differential volume. So dx, dy, dz. So when you want to figure out the mass, we essentially will have to integrate this function right here, and as opposed to just 1 over z, y, and x. So the mass of our figure is something kilograms. And we did that by integrating this 3-variable density function, x, y, z, dz, dy, dx, of these 3 variables. At any given point, there's a value, but not really a direction, and that value is a density. It's just that simple, folks. Math. How hard can it be? I'm out. How many times do I have to tell you to stop eating those stupid M&Ms?
I need a new job.
Taking the volume under a surface. So first of all,
Oh, I forgot the important part.
Oh.
You're not supposed to be reading the script. You're just pretending that you're reading like from this.
let's say that this that's this cut. It depends which, all those sheets that now have depth. If I took the infinite thumb.
I don't know what they pay Bogar so much for. Boundary here come in like that. Come in like what? I wonder what boundary am I looking?
So messy.
I know. I don't know. Good thing I'm not a math teacher. That's my cube. That's a great line. It's not on my script.
It is. It's,
Where?
let's say it's with is dy.
Oh, it's hide is D. I did skip DZ. I've always skipped DZ. But a lot of my markers suck. So this is gonna be interesting. And they don't all smell like chocolate mint. And you might be wondering, well, why are we doing it at all, right? Why would we even do this? What's the point? That's what everyone wants to know. Anyway, so we could say that the mass, D mass, right, D mass. No, it's differential mass is what that is, or a very small mass is going to equal the density at that point. So we have D mass.
When you first say D mass, you write down D mass.
Okay. So they can see what a D mass I am. I'm sick of you eating those dang M&Ms all the time. I got one at you. Trying to teach you life skills, you're always eating those M&Ms.
Still
I don't think I hit any of them.
We're going to integrate from x is equal to 0 and to x is equal to do. Now, we just don't want to.
to do x.
Yeah, I'm just reading what you guys wrote. What did I say? Do?
Yeah.
Well, x could be equal to do too. Okay.
That equals XYZ. So, what are we doing? Mr. Cowan.
You're on fire. You're the best.
This is.
I don't know what you're talking about, but
I
I'm
don't know,
interested.
but it's fun, right?
It doesn't matter.
I don't know what
Just
I'm
watching
doing.
you is entertaining.
Yeah.
I told him, I said, can you believe I got an A in calculus?
Yeah, it's been a while for me too.
It's been a decade.
Yeah, I've been.
You too, right?
A couple decades.
Where did we leave off there? We can assume there's a 1 there.
Right.
Where's picture 7?
Oh.
Picture 7? I'm shading in the top of my cube,
Yeah.
and then somehow my answer is 24. Is that what's happening?
Yeah.
And then voila! 24. It's just that easy, folks. What is this good for? Because this comes out to 24. Where is it? 24.
I think we could have a laugh.
What is that? When do I write 24? Can you believe I actually got an A in calculus in college? I don't know squat.
Can you say I need a new job a little bit louder?
Okay.
I need a new job.
I need a new job!